The question says that a steel wire of length 4.7 meter and cross section area of 3 into 10 raised to the power minus 5 meter square stretches by same amount as copper wire of length 3.5 meter and cross sectional area of 4.0 into 10 raised to the power minus 5 meter square under a given load. What is the ratio of Young modulus of steel to that of copper? So here there are two specimens. One is of copper and one is of steel. Now they both have different length. The steel wire is of 4.7 meter long and copper wire is of 3.5 meter long, and they both have different cross sectional area also. The steel wire has this cross sectional area and the cross sectional area of copper wire is 4 times 10 to the power minus 5 meter square. Now under a given load they both undergo the same amount of deformation, that is delta L, or the change in length is same in both the cases. Now we have to find out the ratio of Young's modulus of the steel. So we know that Young's modulus is the ratio of the stress to that of the strain. Now for elastic limit, till elastic limit, we know that this Young's modulus is constant as per the Hooke's law. The ratio of the strain to that of the strain under the elastic limit is constant, and that is known as the Young's modulus. So and we also know that stress is defined as load per unit cross sectional area. We have to find out ratio of Young modulus of steel to that of copper. So upon formulation of this Young's modulus of steel to that of copper, we write Young's modulus of steel in the numerator, that is the stress in the steel wire divided by the strain in the steel wire to that of the stress in the copper wire to that of the strain in the copper wire. Now we can further simplify the stress as load per unit cross sectional area of steel multiplied with the inverse of the strain, that is L by delta L. Here delta L is the change in length, and we know that delta L for steel and delta L for copper is both equal, so they both will result out to 1. The ratio of delta L of both will result out to 1, and we also know that load given to the both the wires are same, so this will result out to 1 as well. Now upon further simplification, we get the ratio of the Young's modulus of steel to that of copper to be equal to the cross section area of copper multiplied with that of steel divided by cross section area of steel multiplied with copper. So upon solving, we get the ratio to be equal to 1.8. Now when we use these real values of Young's modulus of steel and divided with copper, we also will get the value similar to 1.8. So the ratio of Young's modulus of steel to that of copper is 1.8 as calculated. Thank you.